Students, let us begin with the third video concerned with the topic that is module 3 and part 2 here, that is antenna basic parameters here. So in the last videos we have learned so many things regarding the basic antenna parameters here. Okay, let us try to understand some more parameters in this particular video here. Okay, the first parameter which we wanted to understand is bandwidth here. So what is the bandwidth here? Especially concerned with the antenna we have to define here, right? It is again the same definition here, but with a little bit of some added statement here. That is again the range of frequencies here, which the range of frequencies within which the performance of a particular antenna with respect to some characteristics, okay, is able to adjust and it is going to work according to that one here. That is what you have to mention here, okay, within which the performance of an antenna with certain specific characteristics it is going to work here, right? That is what you can define as the bandwidth of an antenna. Okay, range of frequencies within which the performance of an antenna with respect to some special characteristics it is going to work here. Okay, within that bandwidth itself only we are having to discuss regarding the broadband antennas and the narrowband antennas, how exactly these are classified here, right? So usually, whenever we take or whenever we understand regarding the broadband antennas here, the bandwidth concerned with the broadband antennas can be defined as a ratio of upper frequency to lower frequency here. Okay, so for example, if you take 10 is to 1, 10 is to 1 bandwidth indicates that upper frequency is 10 times greater than the lower frequency. This is how we can specify regarding the broadband antennas here, bandwidth here. Now, if at all we consider the narrowband antennas here, so this particular narrowband antenna here, bandwidth can be expressed in terms of the frequency here, sorry, percentage of frequency here. Okay, difference over the central frequency of the bandwidth here. How much percentage change is there, okay, with respect to the center frequency of the particular bandwidth here. For example, let us consider 5% bandwidth is there here. Okay, so what does it indicates here? Okay, acceptable operation can be done, okay, that is 5% with respect to central frequency of the bandwidth here, either less or more here, like this. Okay, so 5% bandwidth. Okay, now let us understand another two characteristics are there here. That is pattern bandwidth and the input impedance bandwidth here. Usually, this bandwidth is a very important characteristic of an antenna here, which usually the characteristics of this antenna will be very critically affected here by the frequency change here. So, so what happens here is that if there is a pattern bandwidth is there here, okay, usually the gain, side lobe level, okay, beam width, polarization, and beam direction are associated with the pattern bandwidth here. Okay, there is another bandwidth, that is input impedance bandwidth is there. If there is any variation in this particular input impedance bandwidth variation here, there is a change in the characteristics of the antenna, that is input impedance and the radiation efficiency here. Okay, these two are related to the impedance bandwidth here. Okay, the next topic which we want to discuss is antenna temperature here. Okay, antenna temperature here. Now, we all know that the very basic understanding is that whichever object you take here, every object is going to radiate some or other energy here. Okay, if its temperature is above 0 Kelvin here, okay, if its temperature is above 0 Kelvin here, so antenna temperature is not the physical temperature here. Remember, it is not the physical temperature, it is the how much noise an antenna is going to produce in the given environment here. That is nothing but our antenna temperature here. Okay, so usually this antenna temperature depends on what is exactly the gain pattern is there, or the thermal environment is there in which it is being placed here. Okay, so it is also referred as the antenna noise temperature here. Okay, now just for a definition sake here, there is some an equation that has been written here. Whatever the amount of energy that has been radiated here, it is represented by the capital TB here, a T suffix P, which is known as the brightest temperature here. Okay, it is also defined as TBF theta comma phi here. Okay, emissivity epsilon Okay, theta comma phi Tm. Okay, that could also be written as 1 minus whatever the reflection coefficient is there here. Okay, into Tm is there. Tb stands for brightness of the temperature, which will be in terms of the Kelvin here, and emissivity is there. Molecular temperature Tm is nothing but a physical temperature here, that is K, and the reflection coefficient here. Usually this brightness temperature emitted by the different sources is now it has been interrupted by the intercepted by the many antennas here, and it appears as at their terminals as an antenna temperature here. And now this antenna temperature, after it is weighted by the gain temperature of an antenna, is given by T is equal to this whatever the 0 to 2 pi 0 to pi dB. DB is what here? Brightness temperature, gain pattern of an antenna, sin theta d theta t phi divided by the gain pattern of an antenna here. This will give me the antenna temperature here. Okay, the certain points which I have discussed, it is been listed here. Okay. Now again he has defined here for an antenna with radiation pattern, he has defined here. Okay, with respect to the radiation pattern, how exactly the antenna temperature can be taken into consideration here. Radiation pattern is represented by R is equal to theta comma phi here, and the noise temperature is mathematically been defined as T is equal to 1 divided by 4 pi 0 to 2 pi 0 to pi R, that is radiation pattern, and whatever the temperature brightness temperature sin theta d phi here. Okay. Okay, now let us understand regarding the another parameter, that is antenna efficiency. What is efficiency here? Okay, that we have to understand here. How much how much the antenna is efficient here. Okay, how much it is going to transmit the signal here. How much it is efficient here. Right? If at all we consider the input terminals of an antenna here, we are looking into how much the gain efficiency is there here. If at all, if I consider the output terminal of an antenna here, we are trying to understand regarding the directivity efficiency here, how much directivity we are having here, right? So in this case here, we will be having some losses here. That is, reflection loss will be there, conduction loss will be there, and the dielectric losses will be there. All three are represented with the one specific symbol or term here, that is EC. Okay, EC is represented by the conduction loss here. ED is nothing but dielectric loss here. Sorry. And ER is nothing but a reflection loss here. So when does these losses will occur? That let us understand here. Reflection losses will occur here whenever there is a mismatch between the transmission line and the antenna here, right? Between transmission line and the antenna here. Okay, the total efficiency of the antenna that has been given by E naught is equal to ER EC ED here. Okay, what about this conduction losses here? That is given here. Conduction losses plus dielectric losses can also be considered as I square R losses here. Okay, that is ECD here. Okay, ECD it has been there here, where total efficiency, reflection efficiency, okay, conduction efficiency, dielectric efficiency. There is some symbol here. Symbol is nothing but here. This is reflection coefficient symbol here. This reflection coefficient is nothing but we could consider this as a voltage reflection coefficient here. Okay, VSWR is there. But VSWR is nothing but here voltage standing beam ratio here. Okay, that is written by 1 plus the reflection coefficient magnitude divided by 1 minus, actually it is 1 minus the reflection coefficient magnitude here. Okay, by equation 1 can also be rewritten as E naught is equal to ER into ECD. ECD is equal to 1 minus of reflection square here. Right. So ECD is nothing but an antenna radiation efficiency here. ECD antenna radiation efficiency. Now we are going to define that particular antenna radiation efficiency here. So I think it is very much clear regarding the antenna efficiency here. We need to consider the input terminals, output terminals, and these are three reflection losses, or you can say conduction and dielectric losses here. Together we can write equation number 1, and hence could be modified with this equation here. Okay. Well, let us understand the radiation efficiency, or antenna radiation efficiency here. This antenna radiation efficiency, it is going to take into account all the three losses here: reflection coefficient, and conduction losses here, and dielectric losses here, all the three. But usually these conduction dielectric losses are difficult to calculate here, and they are inseparable here. Hence, they are always together dumped here to form ECD here, efficiency. Okay, so now we need to find out the radiation efficiency uh, equation here. Then ECD is equal to RR divided by RL plus RR here. RR is nothing but here your radiation resistance here, right? RL is nothing but here it is the resistance that is being offered by the conduction and dielectric losses together here. So if at all I wanted to calculate the conduction dielectric efficiency here, it is defined as a ratio of power delivered to the radiation resistance RR to the power delivered to the radiation resistance plus whatever the resistance that is been offered by the conduction and dielectric losses here. So that is what is radiation efficiency here. If at all I have a metal here, metal rod whose length is L here, and it is having a uniform cross-sectional area as A here, what is exactly the resistance that has been offered by? Okay, so that resistance is R DC is equal to 1 divided by conductivity into A here. Okay. Okay. So if the skin depth of the metal rod is very small, comparable to the smallest diagonal cross section of the rod here, smallest diagonal cross section of the rod here. So based, if at all we have the uniform current distribution here, then high frequency resistance is written by, this is 1 divided by P into RS. RS is nothing but here conductor surface resistance here. P is nothing but here perimeter of the cross section of the rod here, perimeter of the cross section of the rod here, and RS is nothing but here conductor surface resistance here. Omega is nothing but here your angular efficiency here. Mu naught is nothing but it is permeability of the free space here, and this is conductivity of the metal here, sigma. So resistance that has been offered by the high frequency is 1 divided by P into RS here. You know the RS, that is conductor surface resistance, is given by root of omega into mu naught divided by 2 conductivity here, right? Right. So now this is will be in terms of ohms here. Okay. Now this is regarding the antenna radiation efficiency here, right? Now last but not the least topic here, antenna field zones here. What is antenna field zones here? Usually the antenna field zones are been divided into two here. That is near field or Fresnel region here, far field or Fraunhofer region here. Okay, this is what is the length of the particular antenna here, which is represented by capital L here. Okay, around this particular length of an antenna here, there is an antenna region here. Okay, and uh, and there is a boundary sphere of an antenna region here. That is nothing but a Fresnel Fraunhofer boundary sphere here. This outer circle is called as outer circle boundary is called as a Fresnel Fraunhofer boundary sphere here. Inside this Fresnel Fraunhofer boundary sphere here, we are having something called as a near field or Fresnel region here. Okay, outside it is far field or a Fraunhofer region here. Okay, so what is this Fresnel and the Fraunhofer region? Is nothing but a near field is usually called the Fresnel region, and far field is called as a Fraunhofer region here. Okay, usually boundary between the two here, that is this boundary, the inner circle and the outer circle, between these two circles here will be having certain resistance here, that is represented by R is equal to 2 L square divided by lambda here, right? L is nothing but the length of the antenna here. Okay, lambda is the wavelength here. Okay, now usually whatever the power is there here, power will be not radial here in the near field region. In the near field region here, power will be not radial, and whatever the shape of the field pattern we are going to get here, it depends on the distance here, right? That is nothing but here, the distance between this inner circle and outer circle here. Okay, whatever the far field is there here, the radial component is power flow is having the radial outward here. Okay, so whatever the shape of the field pattern we are going to get from the far field here, okay, it is independent of the distance here. Remember, whatever the field pattern we are having in the near field depends on the distance. Far field doesn't depend. The whatever power flow is there, it is not here. It is not radial, but here in this case, in the far field region, it is radial here. Okay, this is how we can explain regarding the near field and the far field here. Okay, so what we have learned today? Today we have learned certain parameters here. That is nothing but here our bandwidth we have learned here. The bandwidth, just I will make a revision of it here. Just bandwidth we have read, nothing but here. It is a range of frequencies within which the performance of an antenna with respect to certain characteristics or certain special characteristics it is going to obey. Okay, we are having broadband antennas and narrowband antennas. Broadband antenna is nothing but 10:1. Okay, the upper frequency is 10 times greater than the lower frequency. Here in the narrowband, 5% bandwidth indicates that difference of 5% is acceptable, taking the center frequency here. Then there are certain characteristics of an antenna are going to vary here based on the bandwidth here. Okay, what are the characteristics here? Gain, side lobe level, beam width, polarization, beam direction. These are going to vary based on the pattern bandwidth here. Input impedance and radiation efficiency are going to vary based on the input impedance bandwidth here. Okay, antenna temperature we have learned here, right? It's not a physical temperature here. It is how much amount of noise that is being generated by the antenna here. Okay, that is nothing but antenna temperature here. Then we have regarding the antenna efficiency here. The antenna efficiency is dependent on reflection, conduction, dielectric losses here. Okay, right. So there are, if at all we wanted to consider the efficiency of an antenna at input terminal, we need to look into the gain here. If at all I wanted to identify the efficiency at the output terminal, I need to look into the directivity here. Okay, so this is what is the equation given here. Antenna radiation efficiency is dependent on the two losses here, conduction, dielectric losses here. The equation is written here. Okay, then we came to know regarding the antenna field zones here, near field, far field here. Okay, so this is what I wanted to tell regarding certain parameters of the antenna here. If at all you have any doubts here, please